Hello. In the last video, I have talked about how a radioactive material would decay over time, and how after a certain period of time, um, which we call the half-life, it would decrease by half the amount, and then after the same period of time it would decrease by half that amount again. And I've derived a number of equations of formulas which relates to this behavior and this graph. Now in this video, I'm going to make use of this equation to determine the half-life of a radioactive material. Now, more specifically, I'm going to look at uranium-238. Now, the half-life of uranium-238 has been determined to be, let's see, a very long time, actually, a few billion years. Right, the half-life of this is extremely long. It's about a few billion years. How do people actually determine that half-life? I mean, if you look at this graph, obviously, if we can actually plot a graph of the activity of uranium over time, over a few billion years, then we would see the graph coming down, and from the graph we can then read off how long it takes for uranium to fall to half its amount. But unfortunately, we can't wait for a few billion years. We have most of us would have fewer than 100 years. So there has to be another way. So let's now look at this exercise in which I'll give an example of how we can actually determine the half-life based on what we can measure. Right, so suppose that we have a piece of uranium. Let's say this is uranium 2 let's say 238. Okay, so or the symbol would be U, capital U with a 238 on the top left. So this uranium 238 is known to emit alpha particles. So if we can't actually measure the activity over a few billion years, what can we measure? Well, we can measure the activity for a start. Now suppose that we have, say, 1 gram. We have, say, a mass of 1 gram of this uranium. We can measure that with a weighing machine. And suppose that we can measure the activity A, using a Geiger-Müller counter. And suppose that it's done, and the activity was found to be suppose that it's found to be 12,450 counts per second. Okay, suppose that's the total amount of alpha particles that is measured to be coming out from, or estimated from, the uranium source, the 1 gram source. So so we know this. We know that the mass is 1 gram. So what can we do to find the half-life? Well, it helps if we recall the formula that we have seen just now before I clear off the screen, or in the last video. Let me write it out again. Now, there was this formula which relates A to the number of particles. Okay. So if we know that the mass is 1 gram, and we know that this mass number is 238, we can actually find n, the number of particles. Alright, there are 2 or more ways to do that. I'll talk about that afterwards. So, but even if we can find n, okay, even if we can find n, suppose that we find that, this equation would only give us lambda. But what we really want is the half-life. So how can we actually find the half-life? Let's look at another equation that we got just now. We also have this equation: A is equal to A naught, okay, A naught e to the minus lambda over t, lambda times t. Now, if we know lambda, we can actually use this equation to find the half-life. Okay, let's see how we can do it. Now, this A naught here would be the activity when t is 0, and this A here would be the activity after a time t. So how can we actually use this equation to find the half-life? So this is how we can do it, right? So first, before I can even try doing this problem, try finding the half-life from the activity, I really need a formula that relates the half-life to lambda. Let's see how we can get it from here. As I've said, when t is equal to 0, the activity is just A naught. A naught, right? When you put t0 in there, you have e to the power of 0, which is 1. So 1 times A naught is A naught. But now let's think about what happens when t is equal to the half-life. Now, we often use the symbol t with a little half at the bottom to represent half-life. So if you see half, that means half-life. Okay, so when t is equal to t half, that means that starting from the beginning, time 0, you wait for a time that is equal to the half-life. Then let's think about what would happen to the activity. Now, from what we understand about half-life, the activity must come down by half. So if it was A naught at the beginning, then after one half-life, the activity must become half this value. So it's equal to half A naught. Okay, and this is the equation that we could use to relate lambda, which we call if you remember, the decay constant, in case I've not mentioned this before. It's called the decay constant. So using this, we can then find this relation. Now, in order to do this, we have to substitute this information into the t and the a here. So t, if we put t half into the t there, the a here should be equal to half a naught. So let me do this. Okay, so this becomes half a naught is equal to a naught e to the power of minus lambda t half. Now notice that we have a naught on both sides of the equation, so we can divide this out. Just divide both sides by a naught, and we can now solve for t half in terms of lambda. Okay, so what we could do is this. For the e, I'm just going to take log on both sides. Now it would be easier if I start by inverting both sides. So if I take 1 over this, I get 2. If I take 1 over this whole thing, the power would change signs. Then I get e to the power of lambda t half without the minus sign. Okay, and if I now take the log on both sides, I get log 2 is equal to lambda t half. Finally, I can rearrange this to get to make t half the subject. So t half would be equal to log 2 over lambda. So this means that if we know lambda, we can find the half-life, and we can find lambda if we know n, and here is what I'm going to do next. This is what I'm going to do next. Okay, so let's remember this formula. T half is log 2 over lambda. Okay, I shall write it down here. T half is equal to log 2 over lambda. So now let's try and find lambda. So as I said, we must first find n. Now there are two ways to find n. One way is to take to find the mass of one atom or one nuclide. We can do that if we take 238 and multiply by the atomic mass unit. Okay, and then we take 1 gram and divide by the mass of one atom, and we can get the answer. Now, another way we can do it is to know that this number 238 is also equal to the mass of 1 mole of this uranium 238, the mass of 1 mole in grams. Okay, so let me write this down. So the mass of 1 mole of uranium 238 is 238 grams. Okay, so this is something that I've discussed when I talked about ideal gas in a much earlier video. So this is actually the way that I would prefer to do it, because it's the steps is the numbers I have to use are a bit easier. Alright, but you can do it either way. So let's carry this through. So if the mass of 1 mole is 238 and grams, and we have 1 gram of it, this means that I can think of this means that we can find the number of moles. Okay, we can find the number of moles. So the number of moles would be the 1 gram divided by this. So 1 over 238. And therefore, the number of uranium nuclei. Let me write this out in case we get lost in the symbol. So the 1 gram is the mass of the uranium-238. Okay, that's the mass. This is the activity, and this is the number of nuclei. Or we can loosely think of it as the number of atoms, which is basically the same in this case. So N would be the number of moles. It should be the number of moles, if I call this N, times Avogadro, the Avogadro constant. So this is, we know what the Avogadro constant is. It's 6.022 times 10 to the power of minus 23. Okay, so with these numbers we can find the number of nuclei. Two 0.530 times 10 to the power of 21. That's the number of nuclei. Okay. Okay, right, now that we have the number of nuclei and the activity, we can finally use this equation to find lambda. So therefore, from this equation we have lambda equal to A over N, activity over number of nuclei. And we know the activity, we know the number of nuclei. Okay, so we can find the answer. And the answer is 4.919 times 10 to the power of minus 18. Now what is the units for this? Right, A is in counts per second, N is the number of nuclei. So count is not actually a unit with dimension like seconds or length. So we can just say that the unit is over S, right? Just per second. So that's the unit for lambda, and it's basically a fraction per second, or just a number per second, just this ratio per second. So now that we know lambda, we can actually we can finally use this equation, this second equation, to find the half-life. Just substitute lambda into here. Okay, so let me do this now. So this would be log 2 over, so 4.919 times 10 to the power of minus 18. Okay, if we work this out, the answer would be in seconds, because lambda is in per second. Now it's going to be a huge number. You see, we're dividing by 10 to the power of minus 18, so it's going to be a huge number, and it would be easier to understand the answer if we express this in, say, years. Okay, so this would be in seconds. So if I want to convert this to years, what do I need to do? Let's see. I would need to divide by the number of seconds in 1 year. Now, how many seconds are there in 1 year? Let's see. In 1 year, there are 365 days. Okay, and in 1 day, there are 24 hours, and in 1 hour there are 60 minutes, and in 1 minute there are 60 seconds. So this is the conversion. Okay, so if I now use my calculator to find this answer, I would get 4.468 times 10 to the power of 9 years. So more than 4 billion years, and that is the half-life of uranium, which we don't actually have to wait for 4 billion years to find out. We can find out using this method by measuring its activity and its mass.